Hey y'all, so this week we're going to actually really kind of dig deep into the carbon cycle. So I know that you've done, I did this video where we kind of talked about the carbon cycle ins and outs. I wanted to take some time and actually kind of look at all the little parts of that, right? Because it's one thing to kind of go through one video and do these broad brushstrokes, but I actually wanted to take some time and really break down the different aspects to the carbon cycle. And again, that's a really fundamental part of this class, right? So one of the things we've been talking about a lot is CO2 as kind of main driver for climate change. And I really want us to understand kind of the details and how it works. So welcome to actually my greenhouse, right? This is a great place to talk about the Earth's greenhouse. Hopefully you remember what the atmosphere is made up of. We've talked about kind of the major gases that contribute: nitrogen, oxygen, argon, and then a host of other things that we call greenhouse gases. So the primary constituents: nitrogen, just about 80% of our atmosphere; oxygen, just about 20%; argon, a little bit shy of 1%, and then things drop off pretty quickly. We get into the realm of some other gases. So if we look at the kind of lesser components of the atmosphere, CO2, at a pretty dismal percentage, so small that we don't use percentage. We start to talk about parts per million, right? It makes much more sense to do that. CH4, which is methane, nitrous oxide, which you may have experienced at the dentist's office, and ozone, O3. All of these are greenhouse gases. And again, just to review what that means, when we have outgoing radiation from Earth, right? So again, the shortwave radiation comes in, no problem. It's absorbed into the Earth. It becomes long-wave radiation, and as it's trying to escape, these don't really absorb that long-wave radiation, but these do. Actually, all four of these different things absorb radiation in the kind of infrared wavelength, right? Heat. Again, we've talked about a couple of these other things, but really what we're going to be focusing on today is carbon dioxide. Again, it's not the most powerful greenhouse gas. It's actually far from it in a kind of pound for pound sort of analysis, but it is more pounds, right? There's actually a lot of it compared to these others. So it is the primary gas responsible for regulating Earth's temperature. But you guys know that already. So like I said, I want to start kind of breaking this down and looking at the individual aspects of the carbon cycle. The first one we're going to look at is interactions between the atmosphere and the biosphere that is on the surface of the continent, so the land biosphere. So this is the big beautiful dance, right? The big beautiful carbon dance. The balance between essentially plants and animals photosynthesizing and respiring, right? So I just said that big P word that we learned in grade school, photosynthesis, and that's a consumer of carbon. So plants, as they grow, plants consume CO2 as they build their body form, right? They actually consume water and CO2, and essentially the catalyst in this case is sunlight. So if we look at our chemical reaction here, we've got CO2 plus H2O plus sunlight, and then as a result, we have this mess, CH2O plus free oxygen. And this material is like a very general formula for plants, right? It's actually carbon, hydrogen, and oxygen. It's something that we would call a carbohydrate. You've heard of carbohydrates. That's generally what plants are made out of. There's also sugars, but those are like broken down carbohydrates. So actually, it's really interesting when we start looking at this in the long term, right? So remember, I'm a geology professor, and I teach, one of the courses that I teach is historical geology. We talk about the changes of Earth, really at the geologic time scale. And early in Earth's history, there were the first organisms, right, and the first kind of some of the first chemical reactions to produce energy were photosynthesis, right? So photosynthesis shows up on Earth about 3.6 billion years ago, but it was in a vacuum, it was by itself. And so actually at that time, CO2 was being consumed by plants, and nothing was really consuming the plants, if that makes sense. They would just die and decay. Any free oxygen that was produced was very quickly taken up into the environment by things that like to oxidize, in particular iron, right? So the first oxygen that was produced actually was pulled into the ocean, turns the ocean this kind of cool blood red. Obviously that's not the case anymore, right? So CO2 getting back into the atmosphere was really just a matter of decay at that point. So this is a carbon sink, right? Photosynthesis sucks carbon dioxide out of the atmosphere, and it's really important. So the opposite of what we were just talking about, respiration. This is taking CO2 and actually putting it back into the atmosphere, which is essentially the opposite, right? So respiration and photosynthesis are hopefully in balance. And you can see I've got this lovely animal here. What that lovely animal is going to do is it's going to eat carbohydrates, right? It's going to eat plants, whatever they are, right? Eat a carrot, eat a watercress, or a piece of corn, whatever the case may be. And in that case, the chemical reaction produces CO2. So you can see I've got my chemical reaction. My moose made me, or elk, maybe, I don't know, elk or a moose, it's up to you. Kind of made me run out of room here. But we've got carbohydrates plus oxygen, so they essentially oxidize. The result of that is CO2, H2O, and energy. The other thing it's probably important to point out is that there's no real one chemical reaction that we're showing here. Like photosynthesis is a whole bunch of different kind of complicated chemical reactions at the cellular level, as is respiration. These are overarching chemical formulae that just summarize that, right, without getting into all the little details. And generally, if we think about respiration versus photosynthesis, there's no net change in CO2, right? CO2 is consumed to grow into a leaf on a tree. An animal comes by, consumes that leaf, derives energy from it, and then that CO2 goes back into the atmosphere. So the CO2 is maybe taken up for a couple of months, right? Think about a leaf that grows in the springtime. An animal comes by sometime in June, eats that thing. By mid-June, that CO2 is actually back into the atmosphere. So I do want to dip back in and talk about volumes of CO2. In our last video, we talked about exchanges a little bit. Here we're going to talk in exchanges as well, but also large volumes. So generally in the atmosphere, we have about 850 gigatons. That's actually the same thing as petagrams. I think petagrams is maybe a wonky unit to use. 850 gigatons of carbon, that's the weight of the carbon that exists in the atmosphere integrated across planet Earth, which is quite a bit, right? When that's compared to the volume of carbon in the land biosphere, right, we're not including the oceanic biosphere, it's significantly higher, right? You can see 2,500 gigatons of carbon in the land, taken in the plants and the animals, also carbon in the soils. You could integrate all of that. Again, this is the weight of carbon in the Earth's land biosphere. So now thinking about the flow of carbon through these different reservoirs, right? We talked about the absolutes here, right? The volume in each of those different reservoirs in the atmosphere and the land biosphere. Photosynthesis, on an average annual basis, strips out about 120 gigatons of carbon And actually just about that much is given back by respiration. The one interesting thing to think about, though, is that that's not true over the course of a year, right? There are some times of year, well, first of all, most of our land mass is in the northern hemisphere, so we have seasonality. And for some parts of the year, photosynthesis is really ripping along, pulling CO2 out of the atmosphere. Other parts of the year, not so much. But the amount of respiration doesn't really change, right? The amount of kind of animals eating and digesting, that's pretty much flatlined over the course of the year, right? The populations of animals don't go up with seasons, vary slightly, but generally they're steady state. So there's actually about a 6 ppm difference during that season. And this is something that we've talked about before, right? So if you look here, you can see, this is a couple of years of CO2 data in the atmosphere. And we actually see that really from September, October to about May, there is CO2 in excess, right? It's rising during that time because nothing is stripping it out, right? The photosynthesis isn't really plugging along, but during the rest of the year, we see this decline. And again, we kind of get this, just roughly 6 part per million of oscillation between seasons.